Hello, Math 1342, Calculus 2 students. This is extra practice for quiz 3. And here are the sections for quiz 3. It's Taylor polynomials and error and approximation. I have this 4-1 slightly lightened because I don't have a problem specifically from that on this review. But if you recall from that section, it's the same kind of calculation, just the function would be a polynomial itself. So let's begin with number 1 on this extra practice for quiz 3. It's here. We will find the second order Taylor polynomial for this function centered at a equals 1, and then we will use it to estimate a certain value of the function. So whenever I do Taylor polynomials, I always personally begin with this chart. We have k. We have the kth derivative as a function of x. And then we have the kth derivative evaluated at my center. Here my center is a equals 1. And then the final column is the kth derivative evaluated at the center over k factorial. And this final column gives me the coefficients of my Taylor polynomial. Now in number 1, we want second order. And so I need to go down to k equals 2. My function itself, well, it will help me in differentiating to write this as a power. We have 4x to the minus 1/2. And now I take the derivative. This would be minus 2x to the negative 3/2. And then differentiate one more time. We will have positive 3x to the minus 5/2. Okay. The second column, evaluate at the center. Well, all of these with the center is 1. 1 to any power is 1. And so I just get 4, negative 2, 3. And the final step, divide by k factorial. 0 factorial is 1 and 1 factorial is 1. But 2 factorial is 2. It's 2 times 1. So we have 3 over 2. And now I will write my answer. Here's this notation. We have second order, and then the center is 1. Okay, now this part, these are the coefficients, and they go correspondingly with the degree. So here's the degree 0, degree 1, and degree 2. It's 4, and then we have minus 2. Now, don't forget the center is 1. So we have times x minus 1. And then plus, we have 3/2 x minus 1 squared. This is the answer to part A. This is my second order Taylor polynomial for this function centered at a equals 1. Part B, we use this to estimate this function evaluated at 1.15. Now, typically, this one's not too bad. But typically, I will line up what I'm trying to estimate as compared to the original function to get the right x value. So we compare here. Like I said, this one is not too bad. Then you just compare, right? We see that x is 1.15. So we use x equals 1.15. And so that's exactly what we want to do here. We want T2 F, well, we evaluate the polynomial at 1.15. When we do, we have 4 minus 2 times 0.15, because this part evaluated here is 1.15 minus 1, which is just 0.15. And then we have plus 3/2 0.15 squared. Well, the thing is, this is polynomial evaluation, right? Which is absolutely wonderful. Polynomial evaluation. But I get this is approximately, well, 3.73. And then it goes 375. 375. Maybe I'll just round to 3 decimal places and leave it like this. Okay, so this is the end of number 1. Number 2, well, if we look at this problem, we begin with another Taylor polynomial. It's Maclaurin here. And Maclaurin means Taylor polynomial with center 0. In fact, we see that here in this notation. So I start off by making my chart, k, the kth derivative as a function of x, the kth derivative here evaluated at my center, and then finally the kth derivative evaluate the center divided by k factorial. Okay, so this is what I need in this chart. And this last column over here, just like in the last example, will give me the coefficients of this polynomial. Now, third order, okay? If all I needed was the polynomial, I would stop at k equals 3 because we're asked for a third order. But if I look ahead, so right now I am on part A. If I look ahead, you see we need to find a reasonable upper bound on error. And the form of error involves the very next derivative. And so I might as well go ahead and compute the fourth derivative. But this one I'll just use in part B. So I don't need to evaluate at the center, and I don't need to evaluate the center divided by k factorial. I'll just go ahead and calculate this derivative. Okay, well, my original function is ln 3x plus 1. But you see, when we take the derivative here, it's going to be chain rule. Maybe I will come to the side and just for this first step, because we will see this in each step. If we differentiate ln of 3x plus 1, this would be 1 over 3x plus 1, but that's not the end, right? Because here we have this inside function. And the inside function has derivative 3. And so I would multiply by 3 here. Okay, that was chain rule. Now, I'm going to be differentiating again and again and again. And so I'll just go ahead and write this derivative right here as a power. It will make future derivatives simpler. So this is 3. And then we have 3x plus 1 to the negative 1 power. Now, just like we saw here in this derivative where it was chain rule, each time I differentiate, okay, to find the second derivative, third derivative, fourth derivative, I have to remember there's chain rule here. So when I differentiate, I will have a minus 1. This is this bring down the power. And then we would have 3x plus 1 to the negative 2. Okay. The coefficient, though, I have this 3, and then I have another 3 coming from the chain rule. So we will have 3 squared. I'll just leave it in this form right now. Now, we differentiate again. So first of all, we have bring down the power. Minus 2 times here, times this minus 1 will be a plus 2. And then I have, I'll go ahead and write this, 3x plus 1 to the minus 3. But then this becomes 3 cubed because this 3 squared just gets recopied, and I multiply by a derivative of the inside function, which is another times 3. Okay, so here we have the third derivative. Now, I just have one more derivative here. We have the 2. First of all, is going to be negative. Bring down the power will be, let me just write it and we can talk about it, minus 4, okay? Because we have the 3 cubed gets recopied, the minus 3, there's a minus, and that would be a 3 to the 4th when we multiply. But then I have times derivative of the inside function, which is 1 more times 3. And so that's how I get this all together. So this is here. This is my fourth derivative. Now we evaluate all of these at our center, which is 0. The good news here is, here, for instance, 3x plus 1 evaluated at 0 is always 1. So these aren't too terribly bad to evaluate at our center. The first one, we have ln of 1. Natural log of 1 is 0. And then we have 3. And then we have minus 3 squared, which is minus 9. Then we have positive here. It's 2 times 27, which is 54. Okay. Now my final step to get the coefficients of my polynomial, we divide by k factorial. Well, this is 0. 1 factorial is 1. 2 factorial is 2. And 3 factorial is 3 times 2 times 1, which is 6. So I get 9. These are my coefficients. So let's write the polynomial here. This is T3 f x, and my center is 0. Well, we have 0 as the degree 0 term. And then the degree 1 coefficient is 3. And so, well, my center is just 0, so 3x. And then we have minus 9 over 2 x squared, and then finally plus 9x cubed. This is my third order Maclaurin polynomial for the function ln of 3x plus 1. Now for letter B, we suppose absolute value of x is less than or equal to 0.1. And we want to find a reasonable upper bound on error in approximating the function by or using this Taylor polynomial that we calculated in the first part of the problem. So maybe let me just write the interval, because this is important. The interval here, if absolute value of x is less than or equal to 0.1, the closed interval goes from minus 0.1 to 0.1. Okay, this is my interval. Now, the first step in one of these problems is we write down the general form. So we want the third order error, okay, and it has the following form. Well, it would be the fourth derivative at c over 4 factorial times x to the fourth. And the thing that to remember about this is it looks like the very next term, except instead of having 0 here, it's for some c, and we don't know what c is. Our goal is not to find c at all. So let me write that. This would be for some c in this interval, okay, because, well, in fact, both x and c are in this interval, but I will just write it like this, okay? Now, I also, just as a comment, I recopied this. We calculated this in part A because I knew error was coming. So maybe I will take that next step. When I take the absolute value here, and don't forget this, because, for example, if you look at this fourth derivative, it is negative. And the absolute value of that would be positive. So we definitely need the absolute value signs here. So one more step. This would be 2 times 3 to the 5th. This power of 3x plus 1 is in the denominator. So we have 3. Now evaluate at c plus 1 to the 4th. Down here, we have a 4 factorial. And then up here, we have an x to the 4th. Well, I think about this as a two-step process. First, I want to make this as big as possible on the interval. And then sort of second, and also independently, I want to make this part as big as possible on the interval. So I will have 2 less than or equal to's for each step. And then overall, you can say the error is less than or equal to what we have at the end. First, I'll look here. You're only looking on this interval. And, well, this function, okay, what are we going to use for c? If you think about this, the denominator is growing. And so this thing is decreasing, right? The denominator is growing. We have a fixed numerator. And so this is a decreasing function. Let me write that. This is decreasing. If you have a decreasing function, okay, on closed interval, the largest it can be is here at the left endpoint. And so we will use here, we will use c equals negative 0.1. Okay, this will be our first less than or equal to in this two-step process. Let's do that now. Okay, so we would have 2, we would have 3 to the 5th. So far, all of this is just constant. And then when I evaluate this at negative 0.1, you notice I get 1 minus 0.3. 3 in the denominator, well, raised to the 4th. So this would be 0.7 to the 4th power. And then I still have this. I haven't changed this x to the 4th. I mean, 4 factorial is the constant, so I haven't changed that either. This was step 1 in my 2-step process. Now, step 2, we have this part, and you ask, how big can this be on my interval? And really here, you could use either endpoint. So you can use either one, 0.1, or either one is 0.1 to the 4th. The idea on this part, when we're trying to say it's less than or equal to something, move as far away from the center as possible. Okay, certainly when we use the center, that would be 0, and that would not be a reasonable upper bound on error. Definitely not. So here we use really either x, we get the same value. We have 2 times 3 to the 5th. We have 0.1 to the 4th power. And then here divided by 0.7 to the 4th. And then we still have this for factorial. This was our 2-step process. And then, well, here we see it. This is from Desmos, but we can round. And quite often we will round past the leading zeros, for instance. So you can check. This is entered in correctly. And here we have 2 leading zeros, and then maybe I will round to 3 decimal places past that. This would be approximately 0. We have 2 zeros, and then we have 843. Okay, this would be my answer here. Reasonable upper bound on error. We have one more on this quiz extra practice. I understand this part, finding a reasonable upper bound on error. It's usually students find this challenging, and quite often people find this to be one of the most challenging things in this course. And so without a doubt, I wanted to give more than one example of this on our quiz extra practice. This one was almost identical to one on a recent final. We have 3 parts here. We will compute a Taylor polynomial. We will use it in an estimation, and then we will find a reasonable upper bound. So we have 3 things to practice. But this starts the same as all of the ones we have done so far. I make a chart. We have k, the kth derivative as a function. We have the kth derivative evaluated at, well, my center, which is 7 here, and then the kth derivative evaluated at the center divided by k factorial. Okay, and just like we saw in the past 2 examples, this column gives me the coefficients for my polynomial. Well, we want second order. This means I differentiate down to k equals 2. But you see, I realize that looking ahead, I have a upper bound on error. And so I will go ahead and compute one more derivative. My function is x plus 1 to the 1/3 power. So let's start differentiating. We have 1/3 x plus 1 to the negative 2/3. Well, this would be also technically chain rule, but the inside function has derivative 1. Now we have negative 2 over 9 x plus 1 to the minus 5 over 3, and finally positive 10 over 27 x plus 1 to the minus 8 over 3. In fact, I think we did cube root of x in class, and we saw very similar derivatives. But the polynomial will look very different because now I'm evaluating at a different center. I'm evaluating at 7. Here, you notice this is 8 to the 1/3. So this is 2. Now, every time I evaluate one of these, I have to remember 8 to the 1/3 is 2. Here, I have 1 over. It's 3 times, well, I have a squared, right, cube root and then squared. This would be 3 times 4. This is 1 over 12. Okay, great. And then here I have minus 2 over, we have a 9, and then times, this would be 2 to the 5th. 2 to the 5th. I'll just leave it like that for the moment, okay, because now comes when I actually get my coefficients. We divide by k factorial. 0 factorial is 1, and 1 factorial is 1. But now 2 factorial is 2. So this will just be minus 1 divided by this, 9 times 2 to the 5th. Let me come up here and do this. 2 to the 5th is 16 and 2, 32. So let's multiply 32 times 9 to figure out what we have here. We have 8. Okay, we have 288 in the denominator. So this is minus 1 over 288. These are my coefficients. And that's a small fraction, minus 1 over 288, but it's fine. It is part of our polynomial. Now let's write it. This is t is 2f x 7. This would be 2. It's plus 1 over 12 x minus 7, and then minus 1 over 288. We have x minus 7 squared. This is part A. This is my answer right here to part A. Letter B. We use this polynomial to estimate the cube root of 8.2. This is similar to the first one we did. But just like I mentioned in class, I always line it up. So we want to estimate the cube root of 8.2, and we compare it to the function that we found a Taylor polynomial for, which is the cube root of x plus 1. And then you see it helps us solve for the x. So this says x plus 1 will equal 8.2, or x equals 7.2. I'm going to evaluate my polynomial here at 7.2. We want t to f 7.2, 7. When we evaluate this, very similar to the first one, you see 7.2 minus 7 is 0.2. So this will be 2 plus 1 over 12 times 0.2, and then minus 1 over 288 times 0.2 squared. Polynomial evaluation. This is exactly what we love to do, polynomial evaluation. And I get this is approximately 2.0165. Or you could call it 2.017, just depending on how far you want to round it. After the 5, it goes 27777 like this. But I will leave it right here. Okay, this is my answer in B. Now, here comes the fun. The reasonable upper bound on error is next. This question reads, if the absolute value of x minus 7 is less than or equal to 0.2, find a reasonable upper bound on error in approximating the function by this Taylor polynomial. And I just recopied here the third derivative, which we already calculated. So maybe I will begin and write down my interval. Maybe this one I'll draw a number line. You see, we have 7. And what this says is if you are within 0.2 of the center 7, so I would move out here and move out here. This would be 7.2, and this would be 6.8. So this tells me my interval of x values. It's right here, closed. Oh, maybe we can't see that pink. It's right here. Now we can see it a little better. It's from 6.8 to 7.2. Wonderful. Let's write out though what we want. We want the, this was a second order polynomial we calculated. Okay, general form. It looks like this. This would be the third derivative at some c over 3 factorial. And then we have x minus the center cubed. So x minus the center cubed. And this is for some c in this interval here from 6.8 to 7.2. Okay, now, once again, two-step process, but let me do the first part of this, and that's just fill in what the third derivative evaluated at C is. So we have 10 over 27, and then we have C plus 1 to the 8 over 3. In the denominator, I have a 3 factorial, and then up here, I have, well, this time I need absolute values on this, so x minus 7 cubed, because this is an odd power, and so it's not always non-negative, so I need absolute values here. Okay, so far, so good. Well, we have the general form. Now comes our two-step process. The first thing is we want to make this part as big as possible on our interval. And independently, we want to make this part as big as possible on our interval, two-step process. If you look here, it's in fact very similar to the last one. We have a fixed numerator, and then we have a denominator that is growing over our interval. And so this is decreasing. And we will use a decreasing function on a closed, say, interval. The largest it can be is at the left endpoint. So we will use C equals 6.8. This is our first less than or equal to. So I have 10 over 27, and then I have 7.8 to the 8 over 3. I still have a 3 factorial here, and then in my numerator, I have this x minus 7 in absolute value cubed. And I am now on the sort of step 2 of my two-step process. Well, just like I said in the last one, now we want to move as far away from the center as possible to make the absolute value of x minus 7 cubed as big as we can on this interval. And once again, this can really happen at either endpoint. So we'll use either 7.2 or 6.8. Okay, they're both 0.2 away from the center. And this comes our second less than or equal to. We will have 10, we will have 0.2 cubed, and then we have all of this in the denominator. We have 27, we have 7.8 to the 8 over 3, and then times 3 factorial. So this is our reasonable upper bound on error. Now, here's where I entered it into Desmos, you see, we have 10.2 cubed over 27, 3 factorial, and there's a 7.8 to the 8 over 3. And here's what we get. Just like I was saying in the last one, we will typically round past the leading zeros like this. So if I round to, say, 3 decimal places past the leading zeros, I have approximately, how many zeros are there? 5. 1, 2, 3, 4, 5, and then I have 206. And this would be my final answer here. These are fun. I know they're challenging, but if you practice, and there's a few others in the homework, for instance, you can practice, you will have them down, I am sure. So thank you so much for this quiz 3 extra practice, and good luck on the quiz.